one with 15 to 43. It should be noticed that now these two nodes are half full. The node starting with 50 is on the left. I couldn't fit it in the slide, but it's not deleted nor joined with the other values. Simply a new node is created. Of course, this happened with leaf nodes, and you need to make some modifications to the upper level node. Add this value, maybe, as it happens here. Now, it could happen that once you do this, the upper level node is also full, and then you need to do this again. There's nothing very difficult about that, but let's continue with this example. Now, as I mentioned, once the node is filled, it is split in two, and each node is half full. Now, this insert can be perceived by a user making the inserts because it takes more time. Because once he did this insert, a new node was created, so the database had to write to disk, and some new operations needed to be executed. Now, let's make insertions differently. How can we do to turn this leak or this time difference into an attack? So let's imagine that we know a little bit of information about the node here. The node here, it has some values 3, 6, 7, 9, and 10. But let's imagine that the user or attacker knows that it starts with 3, and that the node on the left, which isn't displayed here, starts with 18 or 17, 20, 25. And we make inserts 11, 12, 13 until 16. And once we get to 16, once we get to 15, the node is full. Once we add a new value, the node must be split. So, from the user or attacker point of view, he knows the value 3 and the values 11, 12, 13, 14, and 15. And he knows there's been a split in this page. He knows that the smallest value is 3 and the biggest value is 5, and that each page should fit 10 values. So he can infer that there are other 4 values between 3 and 11 inside this table. He doesn't know the values by themselves, but he knows in which range they are. They are from 3 to 11. Now, this is very interesting because this could be turned into a binary search by simply establishing one range and guessing if the range contains values or not in the database. You can repeat this iteratively, lowering or dividing the size of the ranges or the intervals you are querying, and doing this, you can finally end up guessing the values in the database. Let's see how to do this. So, generalizing what I said, as I mentioned, one can establish a range, and making a few intelligent insert operations, knowing a little bit of the earlier configuration of the database, you can guess if this database holds some values in this range. Why? Well, because the attacker or the user knows what's the size of each page, and by inserting values in each of the upper and lower bound of the interval, he can make it split, and once there's a node split, he knows exactly how many values were placed in this node. Also, it should be mentioned that for our attack to work, we require that the keys are primary, meaning that they are not allowed to repeat. So if you try to insert a key that is already in the tree, you will get an error. This is not necessary to carry out the attack, but it's simpler to explain it this way. So if the attacker or the one executing the attack inserts a value over a pre-existent value, then he guesses one of the keys in the tree, one of the keys in the table. That's what we want to do. We want to get precisely that error.
So it does not require primary. He cannot have
No, for the attack, I'm going to explain now. Keys might be primary. They are not allowed to repeat. However, our attack could be generalized And we made previsions, and we know more or less how to do it. We haven't carried it out, but we have an idea how to do it. But for the rest of the talk, let's assume that keys are primary and they aren't allowed to repeat. So as I mentioned, we want to make this binary search, and it's going to be this way. Imagine the keys in the line as in the upper level, and first we try to decide if the first key in the tree is on the left half, or on the right half of the tree. Once we know it's on the left half, we can divide this in two and guess if it's in the first quarter or in the second quarter. And we continue in this fashion, each time dividing the interval in two and guessing whether there are keys there or not. So what we need, what I will try to build during this talk, is an algorithm that, first, a split detection algorithm. We need to detect splits. This is not evident, and I will show you, at least in MySQL, that you need to do some work. It's not evident how to get to detect splits. And also, one algorithm that, using this split detection algorithm, can tell you whether an interval has keys in its first half or in its second half. So I put here an example to estimate the cost of an attack. Imagine a table holding databases, which are 16 digits decimal value, so it's between 0 and 10 to the 11th minus 1, and that's about 56 binary digits. So assume each page contains about 512 keys, that's 2 to the 9th, and then our attack will need to invoke the binary search procedure approximately 46 times. Why I delete this 10? Well, because once we know in which page the key is, and once this page is smaller in its range than 512, than this page size, then we can search for this by brute force. We need to exhaust only 500 values, which isn't a lot. So let's start with the attack. First, I'm going to explain precisely what scenario we faced. Now, as I mentioned, we are going to execute this attack and estimate and show experiments against MySQL using the InnoDB engine. However, we are confident that our attack can be generalized, since it is only dependent, in principle, in the indexing structure, which are B+trees that are used by other database management systems. However, we only proved the attack against MySQL, and we can only speak for MySQL. So let's start. MySQL, well, you know, it's an open source, very popular database management system used in many web applications, and it allows you to choose from different storage engines. Remember the architecture I showed you earlier? The storing and indexing is done by different storage engines, and one of these, the most popular, is InnoDB. And InnoDB surprisingly uses B+trees to index, and also using this MySQL with InnoDB, we did a clean install of MySQL with InnoDB in a Windows machine, in a Windows XP, populated the database with different sized tables, and try the attack against this, and I'm going to show you results against these differently sized tables. And the characterization of the attacker is that he was only allowed to make inserts to this column. Finally, about noise, let's assume that we did several experiments. In the first experiment, the attacker was using the same machine as the web server where the database was running. But we proved that you can move to another machine in the same intranet, and one switch away, and the attack will still work. So the attack is robust to noise, but we haven't moved any further. And the web server where the database MySQL was running other processes, so there was some noise involved. And you need to understand that since we are measuring more or less the time the disk takes to make some operations, all the services that are running and using the disk as well and the CPU take some time and add noise to the attack. So here's one further example. These are some of the experiments we carried. We carried the experiments against the three size tables with 1 key, 101 keys, and 1001 keys. But the attack scales well, we proved. And we inserted manually one value, this 1013 and 111, and other values uniformly, and we carried out the attack. And here you have the number of inserts made by each of the attacks and the time they took. So more or less, we have this prior estimate for 1400 and 100, and all the attacks took more or less that number of inserts. So the complexity of our attack can be measured maybe by these two values: the time the attack takes and the number of inserts it makes. Now, here all the evidence and all the things I'm telling you are for retrieving one value from the database, but of course you can apply once again this procedure, maybe with a lower complexity, and extract all the other values. So all I am saying is how to extract the smallest value, but you can continue with this and extract the other ones as well. So let's see how the attack works. Something about page splitting with InnoDB. We need to understand how pages are split. Only using the information leak that I mentioned before isn't enough. So we need to understand not only when there's a page split, but also how are the new configurations of each node that is created. So other than following the design principles, InnoDB uses some ad hoc optimizations which need to be understood, and I'm going to explain them for you to carry out the attack. And basically, if inserts are made randomly, uniformly, or following no apparent pattern, then pages are split when they are full, and nodes are split in half. However, if you are making consecutive inserts, then the optimizations will make different create nodes and populate them differently. For example, imagine for 1 second that you have one node which has values 1 to, let's say, 512. Then there's no use in splitting this node in two, since there will be no values. You can store no other values between 256, which is the last node on the left half, and the last value on the left half, and 257, which is the first value on the right half. So in that case, it makes sense not to split the node in two, and that's what InnoDB makes. So let's see. I will need to carry out the attack to these three cases of node splitting, and these cases are there are a few values on the left, and there's a key value I, which we know the attacker knows, and he also knows that there's no value on the right. So the attacker only knows that there's one node which the rightmost, the biggest value is I. Another case is when the same, but when there's only one value to the right, which I call there K1, and the other case is when there are several values, K1, K2. These nodes are not full, and